Now, a solenoid just consists of many loops of wire, or of some kind of current carrier. And actually, I have one over here. Let's see if I can get to it. Before I lose your attention. Now, this is not an official solenoid, but this is a good example. We have a lot of wire wound around this cylinder here. Now, to make an idealized solenoid, you would want to have just one loop of wire around a core, and the loops being next to one another. But they are extended out over some region. Okay, and in the solenoid, one of the important quantities that we have to talk about is how many loops of wire there are per unit of length. So if my unit of length is a centimeter, how many loops do we have per centimeter? I would guess from the weight and apparent thickness of this thing, not that thick, real fine wire, that we have well over 100 loops per centimeter. And if we want to do that in SI units, that'd be well over 10,000 loops per meter. Okay, so anyhow, I'm going to represent the solenoid this way. We got a wire coming in here, and then we start looping the wire. And I'm looping it in such a way that the loop goes like this. Okay, so the loop comes like this, the last loop comes around here and back into the current. So I'm assuming that the current in each loop is counterclockwise as looked at from this direction. Then I sketch something very much like a Gaussian surface, but now we're not talking about the charge enclosed by a surface, but rather the current enclosed by some boundary curve. Okay? And we do a rectangular boundary curve with the lower part of the rectangle, as illustrated here, inside the loops, and the other long side of the rectangle, as I've drawn it, okay, outside of the loops. And we have the short sides. And if we look at the integral around the boundary of this thing, that would be, if we go in the counterclockwise direction, we would go this way along the lower part of the rectangle, this way along the short side here, and back this way along this long side, and then down this way on the short side. Now, whatever the magnetic field is, the symmetry of the situation, and you can read the details of this in your textbook. I'm not going to try to address every picky detail, just give you a good overview, which should be sufficient to raise a few questions that you might well be able to answer yourself, but also give you the picture so that you can understand an explanation in your text or online someplace. These short sides, one, if you go around this loop counterclockwise, one short side goes this way, the other short side goes this way. Now, if you have a uniform distribution of your magnetic field, the integral of the magnetic field dotted with your distance increment, your vector distance increment, is going to be opposite in this direction to what it is in this direction, so the two sides are going to contribute nothing to the line integral because of the symmetry of the field. I haven't gone into detail about the symmetry of the field or why it's symmetric. I might do that, but probably not, because your book talks about it in very clear terms. So you're just left with the integral along the lower half plus the integral along the upper half. But, and again, there's symmetry arguments, other arguments tell you, and I'm not going to detail them right now, but the magnetic field outside of these loops is pretty much negligible. The loops on this side do something opposite to what the loops on this side do, and outside the solenoid, they pretty much cancel out. So you get almost no contribution of the magnetic field to the integral along this part. And all you're left with is the integral along this part. But by symmetry, and by the right-hand rule and everything, you know that the field of each loop is perpendicular to the loop, at least at the center of the loop. And you know that even away from the center, the field is going to tend to be in a direction, in the same direction it is at the center. It might be a little weaker out here than it is in the center. Turns out that doesn't make a lot of difference. And without saying any more about that, I'm going to say that, well, this tells us that the magnetic field anywhere inside these loops is going to tend to be in the direction of the axis, and the way the loops are configured here, that's going to be in the direction to the right here, which we'll take as a positive direction, so that when we do the counterclockwise integral around this loop, we're just going to have the magnetic field multiplied by this length. The magnetic field, again by symmetry arguments, is pretty much uniform inside the solenoid and parallel to this side then. So our line integral of B dot ds here is just going to be magnetic field B times whatever the length of this rectangle is. Now the flux coming through here, well, the field being counterclockwise in any loop comes out at the top of the loop, and it's at the top of the loop where it penetrates this rectangle, comes out in this direction. So that's all compatible, and we can then argue that the flux through here is in the first place positive if we take that counterclockwise orientation, because of course with a counterclockwise orientation you would be using the normal in the direction dictated by the right-hand rule. And also what we're doing is we're summing up the currents that penetrate this region. That's what the flux is, 4 pi k prime times the current that penetrates the region. So let's reason through. The flux through the rectangle bounded by the loop, well, each loop is going to penetrate the rectangle at one point, the top of the loop, and the field is going to be parallel to a normal vector. I mean, the current is going to be parallel to the normal vector at that point. So each loop is going to contribute current I. How many loops are there? Well, we're going to let N stand for the number of loops per unit length. Remember when I had that solenoid or that coil, that coil of wire? I said there may be 100 loops per centimeter, 10,000 per meter, so N would be 100 per centimeter or 10,000 per meter. If you multiply that number of loops per unit length by the length of the rectangle, you find out how many times this occurs, how many loops penetrate that rectangle, so how many times the current I penetrates the rectangle. When you do that, you end up saying that, okay, well, total current penetrating the rectangle is L times N times I. The flux then is going to be 4 pi k prime times the current penetrating the area. Okay, as we say here, 4 pi k prime times L times N times I. Okay, again, N is number of loops per unit length, L is the length, so this is going to be the number of loops, and you get I from each loop. And 4 pi k prime, of course, times I from each loop when you convert this to flux. Okay, so again, the argument field outside is negative, the line integral for the short sides cancel. So the total line integral is just the integral over the side of the rectangle inside the loop, this, which is what I said earlier. Now I ran out of space, but I wanted to stay on the same board, so I went up here. Said, okay, inside the solenoid, the magnetic field, as we already said, is in the direction of the axis because of the right-hand rule, directed to the right because of the right-hand rule and the way I've oriented this, and uniform except near the ends. So as long as you aren't near the end, as long as this rectangle isn't too close to the end, you find that the integral of B dot ds is just B times L. And that's equal to the flux, which is 4 pi k prime times ILN. Well, within here, and not hard to spot, you have an equation that you can easily solve for B. Do you see it? Well, I've circled it. B times L has to be equal to something which is equal to this. So B times L is equal to this. And B is then equal to this expression, which is the same as this, divided by L. The L's divide out. You get 4 pi k prime times I times N. And 4 pi k prime is mu naught. The permittivity of free space. Okay, so that's mu naught times I times N. There's your formula for the magnetic field, as you'll see it in your book, or as you can see it using K prime. And you see the connection between mu naught and K prime.